All right, I'm going to pass it over to you because Jerry's next.
Okay, great. Thank you very much. So our next speaker is Jerry Xuan, and Jerry will be talking about changing subjects a little bit from looking at accelerating objects to giving us early results from the Keck Planet Imager and Characterizer KPIC. So take it away, Jerry.
Hello, thanks. Hi, everyone. So my name is Jerry Xuan, and I'm a graduate student at Caltech. So welcome to Caltech. I'll be sharing results from the early science results from phase 2 of KPIC, the Keck Planet Imager and Characterizer. I'm actually here at HQ in person working on commissioning phase 2, which is why I'm giving this talk virtually, but feel free to reach out to me on Slack or other people listed here, and especially the people in bold who are at the workshop in person. So KPIC is composed of a large team, both in science and instrumentation. For the instrumentation here, I'm highlighting people who've contributed specifically to the fiber injection unit, part of KPIC, which is going to be the focus of my talk today. So with the fiber injection unit, KPIC is enabling high-resolution spectroscopy of directly imaged exoplanets and brown dwarfs. In short, KPIC lives at the interface between the Keck-2 adaptive optics system and NIRSpec, which is a high-resolution near-infrared spectrograph. So KPIC is using single-mode fibers to connect the two, as well as a bunch of optics and mechanical components. And at the end of the day, we get resolved spectra of these exoplanets that show their absorption lines, as shown by this cartoon here. We've mostly been operating K-band, but in phase 2, we also will commission L-band as well. So why are we doing high resolution? So high resolution is a very natural way to go after detailed characterization of exoplanets, which the exoplanet field as a whole has been shifting toward in the past decade or so. So there's a lot of unique observables that you cannot get without high resolution spectra. And because we can resolve these individual absorption lines, or in some cases, emission lines, we can get the radial velocity of the planet, the spin of the planet itself, which constrains angular momentum. We can also robustly constrain atmospheric parameters because we're directly observing these lines and measuring their line depths and relative line depths between different molecules. Finally, with sufficient signal to noise, we can also do Doppler imaging by monitoring the change in absorption lines over time to map out the, for instance, cloud surface of an exoplanet. So there's a whole slew of possibilities here. And in phase 1, we've successfully achieved a lot of our science goals. So I'm showing a summary of the objects that we've detected in phase 1. And there's a lot of objects that have been published or are being published soon. And together, this sample covers a very large range in companion mass and semi-major axis. There are giant planets, such as the iconic HR 8799 system. There's a few high mass brown dwarfs where we have precise dynamical masses. And there's also a lot of objects that live in the boundary between these two populations where we're really not sure how these objects form. So finally, with this statistical sample, KPIC will be able to put some more constraints on planet formation by looking at, for instance, the carbon to oxygen ratio and metallicity of these objects as a statistical sample. So in phase 2, we wanted to keep doing what we were doing in phase 1, but better, and also add new capabilities. So phase 2 has just started, and I'm just going to highlight a few technical goals that we had, which are essentially to increase the number of photons we get from the planets and to reduce the number of photons we get from the star. We also want to enable new science by targeting companions at around the diffraction limit with techniques such as the vortex fiber nuller, which I'll be talking about in a few slides. And in addition, we want to enable L-band science. So after KPIC was assembled and tested at Caltech, it was shipped to Keck-2 and installed there by a team of 4, including Dan, Nem, Tobias from Caltech, and Jacques from Keck. Thanks to their hard work, KPIC was declared ready for science a few months ago. So I've traveled here to Keck in July to help with commissioning phase 2 after the install. And I've worked on several aspects of this here. In July, we had to spend roughly a whole day to do the calibrations because KPIC has a lot of moving components and optics. And that took a lot of manual procedures, and oftentimes there were failures. So something I've been focusing on is to automate that script, automate the calibration process, and make it less painful. And eventually we'll also have a GUI interface for Keck so that the essays can also run this when Keck is facilitized. Finally, I've also worked on automating the data analysis procedure to go from the raw 2D frames to the final wavelength calibrated extracted spectra in just a few clicks. And this is really helping us, especially when we have these long commissioning runs. I'm also working with others in the Keck team to test new capabilities in phase 2, which include vortex chronograph to do the vortex fiber nulling, and also a high order deformable mirror, which helps us suppress starlight. So going back to the Keck commissioning timeline, in July, a team of Keck group members traveled here to HQ to observe in person. And despite some troubles in the calibrations and the difficulty of learning an entirely new system, as Keck phase 2 is very different from Keck phase 1, we had a very successful run in the end with lots of science data. And Dimitri and others were especially happy about this plot. So here I'm plotting the throughput, which is our end-to-end throughput in phase 2 in red, and our optimal throughput in phase 1 in blue. So as you can see, by increasing our throughput, we can get a lot more photons from the planets and basically detect them to higher signal to noise. What's more encouraging is that over the roughly week-long run in July, we saw that our throughput in phase 2 was consistently better than in phase 1. And this is, of course, contributed to by many components, including new optics that were added that have less losses, as well as more clever designs. So with our increased throughput, here I'm showing a small sample of phase 2 detections, where we're targeting these high contrast brown dwarfs and planets. As you can see, the off-axis companions range from about 0.2 arcseconds to 2.4 arcseconds. And we also have a slew of on-axis science that's being led by Luke at UCLA that's targeting hot Jupiters. So please stay tuned for his talk coming up in a few minutes to hear about that. Our increased throughput means that with less integration time, we can get a better signal to noise detection or even similar signal to noise detection. And here I'm showing retrieval results for GQ loop B, where I can confidently detect 13CO, the isotopologue of carbon monoxide in this atmosphere. So on the right are contours for the phase 2 results in blue and the phase 1 results in red, which used more integration time, but provided less good constraints. So that's very exciting. With our increased throughput, we can also get better radial velocity sensitivity. And this is a campaign that will start in phase 2, which is to target exomoons. So just as one can detect planets by monitoring the radial velocity of the host stars over time, Keck is very well suited to detecting exomoons by monitoring the radial velocity of planets and brown dwarfs companions. So in phase 1, we kind of started this by monitoring the radial velocity of one single brown dwarf companion. The constraints weren't very good, but in phase 2, with better observing strategies and our increased throughput, we will be able to push this completeness map down. So I do encourage you to check out Caitlin's poster about this topic, which contains a lot more details. Finally, in L-band, substellar companions are brighter, as shown by the plot on the left. And there's also a lot of interesting molecular opacities in L-band, including from methane. So we collected a few L-band data sets in our phase 2 commissioning runs, and we're working towards the first detection by starting with the wavelength solution, which is all important. Finally, I wanted to talk about the vortex fiber nuller, which is opening a new parameter space of discovery. I think the previous speakers have highlighted this gap in our detection sensitivity of exoplanets, which occurs at roughly a few AU. And here I'm just talking about planets where we can actually detect their spectra and do detailed characterization. So few AU is challenging because for nearby stars, this corresponds usually to the diffraction limit, even for Keck. And so VFN is going to combine a vortex coronagraph and the single mode fibers in Keck in order to null out the on-axis starlight but at the same time allow slightly off-axis companion light, for instance, from a planet to couple through. And this has already been installed in phase 2, and we've started some preliminary tests of it. So I'm working with Dan on this, who is leading the VFN. A few months ago, we targeted a low contrast binary, which had a separation of about 50 milliarcsecond during our observation. And we were able to strongly detect this companion, as well as find a relative radial velocity between the primary star and the secondary star that agrees with its well-known orbit. So in the coming month, we're going to work on better calibrating VFN with a brighter light source in front of Keck in order to actually go down to substellar companion detections. So what's next for phase 2? There's a few topics that a lot of us are very excited about in the KPIC team. So I wanted to share some preliminary ideas with you. First, starlight is still the major limiting noise source for companions close to their star. So we want to reduce starlight contamination with a technique called speckle nulling. As you can see on the left here, even though in Jason's paper, the HR 8799 planets were confidently detected and he was able to do analysis of them, the planet light contribution in red is much lower than the starlight contribution leaking into the fibers, which is in blue. So it would be really nice if we can push these blue lines down, while at the same time keeping the red line to where it was. So this is something that we're doing with our high order deformable mirror, and I'm working with Yinzi and Dimitri on this. In daytime tests with NearSpec, we showed that we can null a speckle at 0.1 arcseconds by a factor of 30. So that means the blue lines on the plot on the left would be down by a factor of 30. And the way this works is we're interfering the speckles with an anti-speckle that's generated by controlling the shape of our deformable mirror. So the two beams interfere destructively. Finally, with better starlight suppression and our increased throughput, we will target fainter planets that we couldn't really access in phase 1. So one of them is 51 Eri b, which is one of the coldest directly imaged planets. It's expected to be methane rich and have a very different atmosphere than other directly imaged objects. So that's something KPIC will be able to explore for the first time. So that's it. And I'd like to thank you for your time, for listening. And I really appreciate the Keck Visiting Scholars Program and my mentors who've supported my visit. I also like to give a big shout out to Shelley and Judy for helping with my visit, also with the conference here. So thank you very much.
Okay, great. Thank you very much, Jerry. Do we have any questions in the room? I don't see any yet on the Slack channel.
Well, I have a hand from Bruce in the room.
Okay, Bruce, take it away.
The higher VM upgrade and nulling speckles, is that to try to null internal instrumental speckles or atmosphere speckles or telescope speckles or what?
Yeah, that's a great question. So of course, in the day, I think what we are limited by will be different from what we will see in like nighttime observing. But some things that we think will be very prominent are actually from the telescope spiders, so the diffraction spikes, for instance. And yeah, I think we just want to try this on sky and see. But for instance, in KPIC, we observe in a position angle mode where so the spiders will come in and out. So that's something that will be interesting to see whether the algorithm can handle that. But the speckle nulling algorithm is will be continuously running. So
how fast is it continuously running? How fast was the update rate?
Yeah, so it's not so it's kind of limited by like the signal to noise we want per exposure. But each cycle right now takes about 5 minutes, I would say.
Very cool.
So yeah, I guess mostly quasi static speckles are being dealt with.
Like I mentioned in the talk before, thank you, Jerry, very much. Wish you could be here.
Thanks.
If we have time for other questions, one came in online from Bruce Baker. asking, is there any benefit to machine learning algorithms to optimize speckle nulling?
I would say probably, but no, we have not explored. We're just using a very pretty basic algorithm now from Michael Bottom et al. 2016. So, but yeah, in the future we are planning to try more sophisticated algorithms, possibly including machine learning.
Okay, thank you.